aren't comfortable with your video appearing in the website, then please turn your video off. And as I say, we like to store our meetings online so that people who aren't able to attend can watch. Our speaker night focuses on a particular speaker and topic, and I'm very honored to introduce our speaker tonight. Just when I was, graduating out of university in the late 1970s, Canada was participating with the development and construction of a new observatory with France and Hawaii. In Hawaii, and this was a huge thing because, you know, we have our Dunlap Observatory in Toronto, we have the Victoria Observatory in Victoria, the large telescope out there. But really, we don't have Canada hasn't really, or had not till then, built an observatory or participated in the development of an observatory in one of the two major places where everyone was building observatories, and that was either in Hawaii on Maunakea or in Chile. And I should say the University of Toronto had a small observatory down in Chile, and that's where Ian Shelton actually discovered supernova 1987. But was, if I remember correctly, was a rather small instrument. So this was a big thing. And I don't think the CFHT is getting the amount of credit that it should. And that's why I'm very glad that our speaker tonight, Beth Laychak, is here to talk to us. She's the Director of Strategic Communications at CFHT. I did not know this about Mary Beth, but she also runs the Maunakea Scholars Program, an innovative astronomy outreach program for Hawaii public high school students. And that's one thing about RESC centers, as I'm sure Mary Beth knows, is that all of the centers are very active with public outreach. I'm glad that that she has that program there, and maybe we'll talk a little bit about tonight. She has an undergrad degree in astronomy and astrophysics from Penn State. She actually grew up just outside of Pittsburgh, and I was telling her how I know a lot of people in the Toronto area are actually long, die-hard Pittsburgh Steeler fans. So, and also they have a very good planetarium down in Pittsburgh. So, but she's, like many of us, she's passionate about astronomy and sharing it with people, and she'll tell us all about what it's like to live in Hawaii. I'm really pleased to pass it to her give her an opportunity to speak to us about our telescope, the CFHT in Hawaii. So, Mary Beth, it's all yours. Thank you.
Thank you so much, Randy. Thank you for that lovely introduction. I am actually at the telescope today. I'm on the summit of Maunakea. I was looking up, my weather tower temperature is 2.3 C. So it's a chilly day. I will explain a little bit later in the talk why I'm up here today and what I'm doing. So
where are you going to camera?
Let me share my screen here. So the title of my talk is Canadian Astronomy at the Top of the World. I very much appreciate the plug for CFHT. We are a going on 42-year-old facility. The telescope is older than I am. And, as Randy mentioned, my title is Director of Strategic Communications. And so my job is fundamentally to explain astronomy to people. I am sitting alone in our control room, which is why I'm not wearing my mask. If any of my collaborators come in today, I will put that on. But for the recording purposes, I'm sitting alone in a room. I will also mention that I am at high altitude. And so when you are at high altitude, your brain can feel a little fuzzy. So I will ask for forgiveness if I get my words a little bit jumbled up at any point. being at the summit of Maunakea is like having 2 glasses of wine before your dinner arrives. Your edges get a little bit fuzzy. Sometimes the words that come out of your mouth come out a little bit jumbled. So this is the first time I think I'm actually giving a presentation from altitude. Usually when I'm up here, I'm conducting summit tours or working on other projects. So I always like to start every single one of my talks with a slide to show exactly where you are and exactly where I am. I feel like 17-hour, 15-minute flight, a little optimistic, but you know, maybe we don't have that long layover that I sometimes run into. As Randy mentioned, we are the Canada-France-Hawaii telescope. And so this is a picture of our facility at the summit. We have been on the summit since 1979. That's when we saw our first light. You can see here, if you notice actually on the side panels, those are our louvers. Those were actually retrofitted about a decade ago. And so what was happening to us is the same thing that happens to many facilities. The warm air inside the dome rises, and instead of having really good crisp seeing directly overhead, we're running into what we call the chimney effect. And so to mitigate that, we retrofitted the dome with these louver windows. And in low wind conditions, and right now we've only got about a 2.5 knot wind. So if that continues, when Lisa begins to observe, she will open up those louvers, and they will act exactly like the louver windows in your house, flushing out the dome. Now, our dome floor is chilled to try to keep it the ambient temperature of inside. Today is a slightly chillier afternoon on the mountain. Usually you see the temperatures at the summit during daytime hours at the 5 sea level. Oftentimes it's around freezing at night. So why Maunakea? Why do you as Canadians have a telescope here? Why in 1973, when Canada and France joined the University of Hawaii, did they decide that mountain? For starters, we're at 4,200 meters. So it's a very, very high peak. Simply put, it's the best site in the world for astronomy. Now, I get pushback all the time from people from Chile who will argue that the Chilean sites are better. I respectfully disagree. There might be more clear nights in Chile, but the best night on Maunakea, I would argue, is simply the best night in the world. But that means no disrespect to Chile, because they have more clear nights than we sometimes do. So for starters, we have a very dry atmosphere above us. At 4,200 feet, we're well above the clouds. We're at about 60% atmosphere. The nice thing about this is I can actually look up at my barometric pressure. My barometric pressure at the moment is about 617 millibars. So if you imagine, you kind of can contrast that with one bar at sea level. So because we have this dry atmosphere above us, we very rarely have any sort of upper level moisture, which is, as you know, what is detrimental to seeing or image quality. The drier, the crisper the air above us, the less potential for those photons coming in from space being disturbed by moisture in the upper levels of the atmosphere. We are usually cloud-free. Whomever is looking at our skies next week or last week may disagree. What we often will happen in Hawaii is in the wintertime, we end up with a lot more moisture in the Central Pacific, which leads to more snow. It can snow year-round at the summit. The temperature doesn't really vary a whole lot, but we have in Hawaii essentially a wet season and a dry season. And so in the wintertime when it's wetter, we tend to have spurts of bad, like extended periods of time of bad weather. And then where we might have a week or two where a storm front kind of moves in before it eventually clears out. We have a very stable atmosphere. As you all know, living in the center of the continent and so close to Great Lakes, that turbulence in the atmosphere that you would get in the springtime or the summertime when those thunderstorms roll in, caused by roil in the upper atmosphere, the idea that, you've got cooling land, heated atmosphere. We are surrounded by kilometers and thousands of kilometers of the Pacific Ocean, which is very stable in temperature. So we end up with a very stable atmosphere above us. very few city lights. So the Big Island is a small rural island. We have a population of about 200,000 over a fairly large area. I believe it's similar to the size of, like, if you're familiar with the United States, like Connecticut, Rhode Island, Massachusetts, maybe all kind of smushed together. We also have very good lighting ordinances. So when you come and visit us, you will notice two things about our street lights. Well, three. One, they all point downward. As you as amateur astronomers know, if you point the light upward, you're really being inefficient in the lighting because it's not lighting the ground that you want, but then you also cause sky brightness. So we have downward facing street lights. We also have two separate kinds of street lights. For a long time, we had low sodium vapor lights that had kind of a reddish orange color. Because of the need for more efficient lighting, the county of Hawaii has moved to LED lighting. However, they're fully shielded LED to block out the bluer end of the spectrum, which leads to our streetlights of having kind of like a greenish yellow sort of color. We also only put streetlights where streetlights are needed. So if you drive through the town of Waimea that I live in, it's a town of about 10,000 people. We have 3 red lights. And the main stretch through town has streetlights, but as you go farther down or farther out of town, we don't see any. The atmosphere at the summit is dry, pure, and clean with no pollutants thanks to the inversion layer. In many pictures of the Big Island or Maunakea or from the summit, you'll notice either a cloud layer breaking up the mountain if you're looking at a shot of Maunakea from sea level, or if you're at the summit, you'll see often a cloud layer. That's where the moist, dirty air of the lower atmosphere meets the cooler, dry air of the upper atmosphere. Dirty air on the Big Island, our main pollutant is Kilauea, the volcano. And so when we have times of higher volcanic activity, we do see that in the inversion layer. But the inversion layer, generally speaking, protects the summit. I say drier air. Right now, we are at about 40% humidity, which is a little humid for the summit. I've had many a night spent observing here when that was part of my job, where the humidity is 10% or 5%, and you can physically feel the water leaving your body. Also, the shape of Mauna Kea. Mauna Kea is a dormant shield volcano. Oftentimes, when we think of volcanoes, we think of Mount St. Helens, or even the one that's currently erupting in Iceland, where you're getting a big volcanic action. Mauna Kea, Mauna Loa, and the entire Hawaiian island chain was all formed over a single hotspot in the center of the Pacific Ocean. As the plates moved, the islands were formed, giving them often a very shield-like shape, hence shield volcano. Recent geological surveys have shown that there is still magma within deep pockets inside the Mauna, but we don't really worry too much about that actively erupting. We've got Kilauea, which resumed its eruption last fall. I actually spent Christmas Eve. It's fantastic. Right now, the crater in the Volcanoes National Park, Halima'uma'u crater, is actually filling up with lava. And so it's fantastic because 1, it's accessible to the public, and 2, there are no homes or anything like that in danger. Now, going back to the shield volcano, because of the shape of that, we get a really good, smooth Larimer flow over the top of the mountain. This would contrast with, let's say, the Rockies or the Andes, which with sharper peaks, you get wind that kind of crashes in and causes that upper atmosphere roil that we talked a little bit about before. So this is a photo taken by a student. This is the Milky Way from the summit. We can see the Milky Way seemingly pouring into Mauna Loa here. And this is a low light image. So over here, we see the moon. And the summit of Mauna Kea is one of the darkest places in the world. When we think of really super dark places, we often think of the northern sites, Denali, for example, but we don't have the aurora. And so with no auroral action, we end up with a darker sky overall than even Denali or some of the northern territories of Canada. This is us. This is a 40-year-old telescope. I'm going to talk over the time lapse. What we see here is the shutter of our telescope opening. That shutter opens like a gigantic garage door. It takes about 8 to 10 minutes to fully open. Cfht is an equatorial mount telescope. We can mount instruments at either the top, like you see here, or at the Cassegrain at the bottom. So as I'm sitting here in the telescope, we have a secondary mirror on at prime focus, and then at CAS, we have Spiru, which is our planet hunter, which we'll talk about more in a minute. As the dome opens, you will notice that the dome will start to rotate, and we are going to see those louvers that I talked about kind of move and open up off onto the sides. All right, we can see we move the telescope to point towards east, so that we move the dome to point towards east so that we can begin the process of flushing the dome without the risk of too much sun. Now moving towards us is our telescope. It moves in both declination and RA. And right here, you can see our 3.6 meter mirror. So the instrument on top is Megacam, and we'll talk about all of our instruments more in a little bit. This is one of my favorite photos. My coworker, Tom Benedict, took this. This is a selfie. He was actually standing at the top of our dome while taking this photo. Now, it wasn't just a selfie for he wasn't doing it for the gram. He was actually doing a panoramic image of the summit for some modeling. He wanted to come down later. So let's talk a little bit about our science. This was the first image ever taken of Cfht. It was a globular cluster. It was taken on August 7th, 1979. That year, the IAU meeting was actually meeting in Montreal. And so the team behind Cfht and Canada in general wanted to really take a good image and show it off at that IAU meeting. This is an image that we can take today. Now, I am cheating. I did not pick any old random image off the telescope. This picture is part of one of the large surveys. And this is actually, if you're familiar with the group Stephan's Quintet, this is Stephan's Quintet. Now, this is an image taken with Megacam, our wide field optical imager. Now, the team that was working with this program, one of the team members is Jean-Charles Pouillon. So Jean-Charles, if you're familiar with any of the Cfht images or the Cfht calendar, that's Jean-Charles's work. And so this image here is a composite of probably about, so I'm going to say 15, maybe 21 to 28 different images. We take 7 images in a red filter, 7 images in the blue filter, 7 images in a green filter, and then they're stacked on top of each other with the color added appropriate for that filter. Now, this data was also reduced in what we call our low surface brightness mode. It's an option that astronomers have to use the combination of a special set of observational techniques combined with data processing to really highlight objects with low surface brightness. So here, this is where we begin to see some of the galactic cirrus and the galactic halos that exist within some of these clusters. This image, which you will also notice is my background, is the Cfht Legacy Survey Deep Field. So I started working at Cfht in 2003, and my first position here was service observer. So Cfht in about 2002 moved from what we would call classical observing to Q observing. Now, classical observing is what you think of when you think of observing with an observatory. Tonight, there is some astronomer in, I'm going to say California, who is getting ready right now to actually start preparing for their night at the Keck Observatory. They have been allocated, let's say 3 nights, the March 26th, 27th, and 28th. Those nights, they're able to do whatever they would like. Now, in terms of their observations, they submitted a proposal for a specific set of observations, and it's their job to execute them over those nights. Now, let's say that it snows tomorrow. Knock on wood, no jinxes. They lose that night of observing, and there's no makeup dates. No one cares that you lost your night of observing in terms of like, oh, I'm so sorry, Randy, you were our top ranked program. Let's just ask Dennis to give up his telescope time. Dennis is not giving up his Keck time for you, Randy, I'm sorry. And I can imagine in my brain, Dennis is shaking his head, yes, like, sorry, Randy, you're out, man. So at CFHT, we do it a little bit differently, and that we do this queued service observing. So if Randy had these, instead of having 3 nights, he would have maybe 16 hours. And so it's our job at CFHT over the course of an entire 6-month semester to execute Randy's programs to his exact specifications. This allows us to do really big seminal science works like our legacy survey. So this deep field here, if we zoom in, you see almost everything in this image is a galaxy. We have 3 slightly saturated stars. And if we go in even further, everything in this series of images are galaxies. We go from galaxies that are very distant, that are just tiny red specks, to these closer galaxies where we can actually start to make out some of the barred spiral features. Now, the Deep Legacy Survey, it's one of its main science targets was to actually look for type 1a supernova. So type 1a supernova occur when you have a core of a star, a white dwarf. So when our sun reaches the end of its life, it's going to expand outward. Well, first, all stars are in perfect balance. Gravity pulls inward, energy and pressure pushes outward. At some point, all medium-sized stars like our sun, they will lose hydrogen fuel in their core to turn into helium. They'll stop producing as much energy, and then the star will contract. That contraction will cause the core to heat, and you'll get a burst of fusion, helium fusion, that will push out the outer layer of the star. We often see this as a planetary nebula, leaving behind a white dwarf core. Now, that white dwarf core has a very, very strict maximum mass, 1.44 times the mass of the sun, the Chandrasekhar limit. If that star, that white dwarf, has a companion that it's orbiting, let's say a larger star that it can accrete material from, it might surpass that Chandrasekhar limit and explode in a type 1a supernova. Now, the beauty of these supernova is because it occurs with a very precise process, we can use them to measure distance to galaxies because they have a standard brightness, what we call a standard candle. So during the legacy survey, they just detected 504 type 1a supernovas and were able to measure the distance to them. And part of that work was part of the larger type 1a supernova work that led to the Nobel Prize winning expansion of the universe theory. Now, this star, I'm going to take a drink of water real quick. Speaking of a really innovative way to use CFHT, we have excellent weather. The good weather on Maunakea, the bad weather on Maunakea is better than a lot of other. So this program, it's called the Pristine Program. They use the telescope when our image quality is not as good. It's over 1 arcsecond. And what they're looking for is early stars. So the survey is called Pristine because they're looking at stars that are ultra low metallicity, stars with almost nothing except hydrogen and helium. So at CFHT, they use a very specific filter. It's called the CAHK filter. And they're looking for stars that have very little light in that filter compared to other ones. And if we take the spectrum of the star here, what we can actually see is the comparison between the pristine star and the spectra of the sun. So we're looking at almost no elements outside of hydrogen and helium. We've got our hydrogen lines here. We've got maybe a little bit of the calcium line here. Back to some hydrogens, our calcium triplet. But you compare that to the spectrum of the sun, and we can tell from this that the pristine star that was discovered is a much, much older star. Now, these observations, along with this dwarf planet RR245, these were made using our wide field imager Megacam. So Megacam is a 1 degree by 1 degree imager, 1 degree by 1 degree imager on the sky. It's the equivalent of 4 full moons. It's often used for survey work. In addition to really looking to see, like I said, with pristine before and the low surface brightness. So this discovery was made by the OSIS team, the Outer Solar System Origin team, Outer Solar System Origin Survey team based around the world, but predominantly at NRC Pittsburgh, University of Victoria, and University of British Columbia. Now, for whatever reason, my GIF here stopped playing, so we're not able to see, but this is actually a discovery image. And what the OSIS team did was they looked at a couple of segments around just off the ecliptic to look for small icy bodies in the Kuiper Belt and beyond. So over the course of the OSIS work, this is actually here, 2015 to RR245, we can see that it has an exceptionally elongated orbit. Generally speaking, though, with the OSIS survey, by discovering about 810 new objects, they were able to detect some patterns. Here we see this gap. This gap is in the 3 to 2 resonance ratio with Neptune. So much like we see with the Kirkland gaps in the asteroid belt, Neptune's gravity definitely influences the placement and the orbital position of objects within the Kuiper Belt. Now, this team, you will often see the OSIS team talk about Planet 9. They are in a different camp from Mike Brown and his team at, I believe he's at the Caltech, or University of California System. Apologies, Mike, I don't remember where your home institution is right now. So they are firm believers, Mike Brown and his team, in the existence of a Planet 9. The OSIS team disagrees. They feel that the 804 objects that they discovered are just the tip of a much larger iceberg. And in fact, there are a lot of small icy bodies outside Neptune, trans-Neptunian objects, Kuiper Belt and beyond, that combined gravity can cause the mathematical deviations that we see in some of the orbits, particularly of Neptune, that leads to the hypothesis of Planet 9. The single best way that I heard one of the OSIS team members describe this is, if you're driving down a highway and you see deer on the side of the road, you're not seeing all of the deer in the forest. There are many more deer in the forest than we see on the side of the road. And they really feel that that is what we see here in the outer solar system. This is a great image of Megacam, taken by Megacam, again showing sort of the capabilities of the instrument. We have Andromeda here and M33 over here. And generally when we look at Andromeda, we think of this little bit here. This project, it was called PANDAS, the Pan-Andromeda Archaeological Data Survey. They were looking at the extended halos of both Andromeda and M33 to do some sort of galactic archaeology, figure out what were we seeing in terms of tidal disruption, tidal forces, galactic cannibalism, and how could that potentially be applied to our own Milky Way. Now, switching instruments, WIRCam is our wide field infrared imager. This is one of my favorite side-by-sides. Over here, we have the classic optical Orion Nebula photo. And then on this side, we've got the infrared. And so I feel that this slide really summarizes why astronomers look not only in the infrared, but in all other wavelengths. In the optical image, we're obstructed by the cold dust, and that blocks us from really seeing some of the central star formation, seeing deeper into that nebula. This is one of my favorite discoveries that I've been a part of. My job is to write the news releases. And so one of the coolest parts of my job is that I often know about things before they're made public, right? And these little guys, this whole trio of systems, this is a brown dwarf. I'm just gonna call it 2MASS AB for the sake of this talk. So 2MASS AB here is a binary brown dwarf pair. And this was Trent Dupuy and Mike Liu, a team that worked together at the University of Hawaii Institute for Astronomy, although I believe Trent's now in Edinburgh, is still working with Mike Liu. So they were looking and observing the very precise positions of these two orbiting brown dwarfs. And in their larger WIRCam image, they actually discovered this object here, 2MASS C, which is a planet orbiting a binary brown dwarf system at an extended distance. Now this planet has a composition that's very similar to sort of the prototypical Beta Pictoris b, The news release actually referred to it as the doppelganger. And so what was most fun about this was it's a cool discovery, but Mike and Trent really weren't quite sure. Are we calling this a planet? Are we calling this an object? What does doppelganger mean? And so we went back and forth on that many times before we settled on planet. Next up, sorry, that tea was much hotter than I thought it was there. Espidons. So espidons is our optical spectrograph / spectropolometer. So what espidon does is it's able to take not only the light from a single star, break it into its component rainbow, but also give information about the magnetic field of that object. This is the Omega Centauri. So many of you may be familiar with Omega Centauri globular cluster. This team, led by Radago Abada, used espidons, and they looked at stars both within the Omega Cent and off to the side that looked like a trailing edge. What they discovered is that there are tidal streams coming off of Omega Centauri, and that leads them to believe that Omega Centauri is not a true globular, but rather the core of a dwarf galaxy that has been tidally stripped through galactic cannibalism by our own Milky Way. And so the observations with espidons combined with Gaia positioning data showed them that the composition and the velocity of these trailing stream were very similar to Omega Centauri, leading them to come up with this hypothesis. Now, I'm going to pause this. Oh, no. Sorry, pause this. So CTEL, our next instrument, and this is the one that in September, Dr. Laurie Rousseau-Napton will be talking about more in depth. She's the instrument scientist for CTEL. Now, CTEL is our imaging Fourier transform spectrograph. So it takes a picture of space, and then through the magical hand-waving math that are Fourier transforms, converts the image from every single one of those pixels into a spectrum. So this adds a three-dimensionality to our image that we're unable to see in a typical Megacam image. But it also gives us many more pixels and more spectra than we would get with espidons. So what we're going to watch here is I'm just going to let it run once, and I want you to watch both the bar on the side, and you'll see very specific spectral lines highlighted, and then you'll see the galaxy in the center, and you'll get the power of CTEL. So as you notice, when we hit each of those nitrogen lines, the H alpha lines, and then here again, sodium, we're seeing the motion of gas. What we're looking at here is a galaxy with a supermassive black hole in its core. When we're hitting that nitrogen, hydrogen, and sodium, what we're seeing in those lines is superheated gas that's being ejected from high speeds from the area surrounding that black hole. We know it's not coming out of the black hole, but in the immense, magnetic fields and accretion disks that's surrounding the black hole in the core, supercharged, superheated gas is actually leaving the galaxy itself. And that's the kind of research that can be done with CTEL. Laurie will talk much more in depth about her large program signals. What she studies is star formation regions in galaxies an intermediate distance away. So not our nearest neighbors, but we're also not looking at anything that's deeply redshifted. Our last instrument is Spiru. Spiru is our infrared spectrograph. Similar to espidons, it also is a spectropolometer. It's also a high precision velocimeter. Our goal with Spiru is to be able to get down to the resolution of 1 meter per second. Simply put, Spiru is a planet hunter. But we're looking for planets around cool M dwarfs and very young planets. So those of you that read my column in the April RASC journal, you will see about AU-MIC-B. So AU-MIC-B is a planet that was discovered by the TESS spacecraft. So the way that TESS discovers planets is through the transit method. So if I take my coffee cup here, my teacup, and we pretend that this is a star, and we have a planet moving in front of it, when I get here, my planet, my star, loses a little bit of light. We see a dip in its light curve due to the presence of a planet. So from that, we can get a good constraint on the radius of the planet, but not the mass. So what Spiru has done is it does follow up on a lot of TESS or Kepler objects. AU-MIC, the star itself, is a young star. It's about 22 million years old. It is highly active, as many young stars are, with star spots, very intense magnetic fields. And so what Spiru is doing is looking for the wiggle in that star caused by the gravity of planets. Now, oftentimes when we think of gravity, at least in terms of, stars and planets, we think of it as a one-way street. The sun's gravity holds the Earth in its stable orbit, and we orbit around it. But there's a gravitational force from the Earth back on the sun, and that causes the sun to wiggle back and forth a very, very tiny amount. What Spiru is doing is detecting that tiny wiggle caused by the gravitational influence of a planet around a surrounding star. Now we can look up here, you can see this is the stellar rotation period, so the star rotating. And then there's this little dip. And when we kind of look at that little dip, what they were able to actually see was a periodicity due to that planet. Now, I was really excited because this was a fun news release, and they were able to determine the mass of the planet. So once we have a mass and a radius, we can calculate a density. And the density of AU-MIC-B is similar to that of Neptune. So we're looking at a large, hot super Neptune. What they also found was the inclination of AU-MIC-B's orbit around the star was very much in line with the star's ecliptic plane. So this is telling us that this planet formed farther out in the star system, and then through some sort of gravitational interaction, moved forward into its stable orbit much closer than the orbit of Mercury right now, to its host star. So this is really helping to not only constrain a planet, but also helps us understand more about planetary formation and planetary formation modeling. Now, a very large part of my job is community engagement. So I had created this slide a couple years ago because I write a board of directors report every year. And this was my ancillary slide to my board of directors report. So this was the activities that we had done within the span of probably 3 weeks. Obviously pre-COVID. I don't know the next time I'm getting elementary school kids in an inflatable planetarium. But the activities that we kind of do are really run the gamut. My coworker, Matt here, he's one of our computer programmers. So he was teaching teachers, doing a workshop for teachers on how they could incorporate sort of a programming mindset and that sequential mindset and sequential thinking for kids as young as kindergarten. And how do we get somebody to move like we would need to move a robot or a computer? A lot of these pictures here are from our annual star party. Some of you may have seen our star party online this year. If not, I can send you the URL and you can go back and watch it. We did completely virtual star party. So each day we had a different video of a talk. So Mark Barrow, who's one of our engineers, he gave an avid amateur astronomer. He gave a talk about buying binoculars for Christmas. So often people, you guys, amateur astronomers, are asked, what kind of telescope do I buy? And Mark really recommends beginning with binoculars because it's a lower cost sort of introduction and investment. I did a craft activity. We did a Q&A with one of our remote observers. We did a live Q&A with 2 of our astronomers, Nadine and Lori. And our director read 'Twas the Night Before Christmas by his fire. So that was kind of our fireside activity. And all of that culminated in a virtual stargazing party that all of those videos are accessible online. In the introduction, Randy mentioned Maunakea Scholars. So Maunakea Scholars is my baby. It is a student-driven research opportunity for Hawaii public high school students to use the Maunakea observatories to conduct their own astronomical research. In Hawaii, we have a massive discrepancy between public school education and private school education. I live in Waimea. The closest high school to me in Waimea has a tuition of about $25,000. And that's if you're not boarding. The local public high school that is about 15 miles down the road, they do not have a tuition of $30,000 per student. And so what you see in the opportunities for students is vastly different. So we choose to work with public school students, and as we grow the program, we'll likely include charter schools as well. So the students and the teachers have the freedom to put Maunakea scholars in their program however they would like. They can do it as these are all in my schools, they can do it as a program where it's an after school club, it's part of their AP STEM class. One of the groups that I work with, it's part of their credit recovery program. So these are students that need science credits to graduate and have gotten to their junior or senior year, either being told by the world or feeling by the world that science isn't their thing. And what we aim to do with them is to see the difference between learning science and doing science. So pre-COVID, I had a very robust active program, my 13 schools, working with having a school on every island, and working with some of the most rural communities in our state, Molokai and Lanai. Oops, poor transition. So the honorarium that I am being offered for this will be donated to Maunakea scholars so that we can bring students to the telescope, we can provide them with additional programming, really pool together our cultural aspects of the program into something that's more robust and less dependent on face-to-face instruction, which is one of the things that we've really realized in COVID. Another program that I want to highlight is Ahuahea Noa, which means essentially to call forth to name. So you all may be familiar with Povehi and Oumuamua. Povehi was just back in the news again. So in 2017, a hui got together, and a hui is the Hawaiian word for team. A hui got together with the idea that objects that are singularly unique or kind of landmark discoveries made from Maunakea should have Hawaiian names. And so our director, Doug Simons, reached out to Kaiu Kimura, the executive director of the Amilo Astronomy Center in Hilo, and her uncle, Dr. Larry Kimura, who works at the Kahakaula College of Hawaiian Language. And so Uncle Larry, he named Oumuamua. And the name for Oumuamua translates to a scout or messenger or traveler from a great distance. Povehi then was named the adorned fathomless darkness of creation. So Po in Hawaiian mythology is sort of the darkness of creation from which everything's from. Now, the Ahuahea Noa program is more than just these two objects. 6 objects have actually been named by the team. And it's been named by a combination of, well, there are these 2 objects, and then there were high school students who got together, they toured the summit, they got an immersion in more Hawaiian language. They were all Hawaiian immersion school students, so they were already fluent in Hawaiian. And they sat down and really understand from Uncle Larry the process of naming. He did the same thing with Hawaiian immersion school teachers. Now, this is not an astronomy project. This is a Hawaiian language project where astronomy just gives the input. We give the space rock or the black hole and say, you know, this is an object that needs a name. But really, we see it as a program that's deeply rooted in Hawaiian language and the practice of Hawaiian naming, which is something that's very deeply important culturally. You can follow us on social media. Generally speaking, astronomers tend to like interact with us on Twitter. That's where I'll find out so-and-so published a paper. We do have a very robust Instagram and Facebook page as well. And all of these materials you can go and take a look at. Now, I mentioned that I'm sitting at the summit today. And the reason for that is we are filming a 360 virtual tour. So if you're familiar, and I know that Curiosity Rover just put one of these out, where you've got a still photograph and you can kind of pan up, pan down, mouse click this way, mouse click that way. And that's what we're creating at the summit. Actually, while I'm sitting here giving this talk, my coworker Rayson is in our machine shop filming. So we're really looking forward to that. Stay tuned. It'll be a big announcement on social media. Super excited about it. We'll also have, in addition to a narrated 360 video that makes you feel like you're on a tour with Rayson and I, we'll also have some still photographs that allow people to kind of look up and around in different areas. So this is our CFHT team. This is a photo from 2018, so I should probably update it. All of my Canadians are circled. So at CFHT, we have a staff of about 45 people. Roughly a quarter of our staff are astronomers, and everyone else does everything else. So Rayson, that I'm up here with today, is a mechanical engineer. Cam right here, Cam's from Nanaimo. Cam started off as one of our remote observers and has recently received a promotion where he's acting as almost like a technical liaison between the needs of the night staff and the technical staff, specifically the software group and our computing program. Over here, this is Kevin Ho. Kevin is the head of our instrumentation group, our engineers. Looking front row here, this is Jane. Jane is our former controller. She is retired. She's retiring like next week, I think. She's been coming in part-time since the first of the year. So with that, if you want to learn more about CFHT, these are all of the different ways you can find us on social media. You can go to our website. You can email me directly. If you want, you can follow me on Twitter. I don't have the most exciting Twitter account because I manage not only the CFHT social media with my coworker Callie, but the larger Maunakea Observatory's social media. So I don't always tweet for myself. So with that, I will stop my share, see if anyone has any questions. Mahalo to Alan for putting in that discovery image available for our R245.
Well, thank you very much, Mary Beth. And I really learned a lot about the telescope. And I'm sure many of our members have questions. So if we could type questions into the chat, that would be great. I wanted to start off and just ask you about how the Canadian team and I guess the French team and the US team, how do they work together? Do they have a specific time on the telescope? And is there a transition between, say, when the French team takes over the telescope? Do they modify it with their different detectors, or is there some sharing of detectors, or how does that work?
Actually, no. So we're seamless because we're in Q observing mode. So as a Canadian, 42.5% of my salary is paid by you. So thank you. Thank you. Thank you. And 42.5% of our time is allocated for Canadian astronomers, a similar amount for the French. And we don't actually work with the entire US community, only the University of Hawaii. And so because we're operated in Q observing mode, we have instrumentation runs. So Spiru is going to be on the telescope for essentially 2 weeks. Every single night we have observations. Every single night we have observations from astronomers, more than one astronomer. So it's not, this person gets this first half of, we switch instruments or switch programs. We do that regularly on the fly throughout the course of the night. So with Megacam, we might be looking at near Earth, trying to detect a near Earth orbiting asteroid for Richard Wainscoat, an astronomer at the University of Hawaii. That observation might be immediately followed using the same camera by Jean-Charles, who's doing a large program called CFIS, where he's doing U-band and R-band mapping of the Euclid fields. And that might be followed by a graduate student thesis from Canada who wants to look at dwarf galaxies. And so that's just kind of a seamless transition. It's the job of our Q coordinator every night to make the Qs, make the plans for the night. They usually have a good seeing, bad seeing. Oh boy, we call that our snapshot programs. excuse me, that's where our calendar images come from, actually, the not great seeing times.
Yeah, right, Beth.
Yeah, so like I said, not great seeing on Maunakea is one.
Stick it on the calendar.
I bet you would all kill for 1 arc-second seeing outside of
Oh, would love it.
So Alan, to answer your question, the way that they were able to tell about this migration, and the Spiru one was an M dwarf, so not quite a brown dwarf, it's an M dwarf. So when in our models of planetary formation, to have enough material to form essentially a gas giant planet, you have to form at essentially the distance of Jupiter or farther. We look at our own solar system, the terrestrial planets are too close to the sun and too warm during formation to have been able to trap those colder gases like hydrogen and helium. So we know that larger planets have to form past what's called the frost zone in a star system. However, this planet is closer than Mercury. So that tells us that at some point in the 22 million years that the star existed, which seems like a lot, but is like a new, like a couple-month-old baby, if we put it in human terms, that sometime during that period, that 22 million years, the planet formed at, let's say, the distance of Jupiter, and then gravitationally moved inward. And so this is giving us constraining the amount of time that it actually takes to form planets and have that planetary migration move in. So I hope that was clearer. We can tell about where the planet formed based on its size. I'm gonna do Ed first. Do workers go home every day? Yes. So when I leave, so today's a holiday in Hawaii. Today is Prince Kohio Day. He was the Merry Monarch. So Hawaii was a kingdom up until 1893. So we have holidays for some of the former monarchs. If I wasn't here today, no one would be at the telescope. All of our observations are actually conducted in our remote observing room in Waimea by one person. So when I leave today, no one's going to come back to the telescope likely until Tuesday. And our day crew, our operations group that is responsible for maintaining the telescope and the building, they pre-COVID did basically 4 10-hour days. Now with COVID, they do 3 10 hours and an 8. With COVID, they do 3 10-hour days, and then they work from home remotely on Fridays, having meetings, working on designs. Our night observers, so our remote observers, they do 5-night shifts. So they will work every night for 5 nights by themselves in Waimea from sunset to sunrise. And then they're off for 15 days. They all have other duties that they do in that 15-day time. Rob, we truck water up. We truck non-potable water up. So all of the water that we drink at the summit, like this, either comes in like water cooler jugs. We have 20-gallon water cooler jugs, and we also have some disposables. But to flush our toilets, potable water is brought up in a truck. So going to what the most significant discoveries made by CFHT are. There are a bunch. I would say the work that I mentioned earlier with the supernova, the type 1A supernova, those discoveries kind of leading towards, oh my God, I'm sorry. Above me is my outside camera, and someone brought a dog to the summit. So I can see a dog on a leash outside. It just threw me for a minute. Don't bring your dog to the summit, please. Please, please, please don't bring your dog to the summit. Anyway, so that type 1A supernova.
Mary Beth, I have to ask, do dogs have more problems with the high altitude than people?
I don't know, but I think it's a bad idea to try and find out.
Yeah, I think so. Sorry, I had to ask.
Yeah, no. I was the one who did the non sequitur as I saw a golden retriever on a leash go dry. I will turn so you guys can see a little bit of what I'm seeing. So I have these cameras above me, and it's just the way that my screen lined up. Anyway, sorry, Swampa. Back to our discoveries. So that type 1A supernova legacy survey really played a critical role in that confirming the hypothesis of the expansion of an accelerating universe, that the universe was accelerating outward. We've been on the forefront of a lot of instrumentation in terms of like Megacam. It was the largest imager. I would say It was the largest digital camera in the world for about 3 or 4 year period. I would say Oumuamua was a really significant discovery. A lot of our work with asteroids, about 50% of the comets and asteroids that are discovered using a combination of pan-stars on Haleakala on Maui and Cfht. Also some in the 90s, some work on gravitational lensing. I will say and give a shout out to Canadian Gordon Walker. When Gordon Walker was doing spectroscopy in the 1980s, he in all likelihood discovered the first exoplanet. That data was not published as an exoplanet, and therefore the discovery in 91 and 95. But in all likelihood, he used Cfht to discover the first exoplanet. It just ended up being, from my understanding, it was one of those things is that like instrumentation wiggle, or is this a planet, guys? And the statement extraordinary evidence, extraordinary claims require extraordinary evidence, and they just weren't as confident in it. Subsequent observations have proven that it was in fact a planet. What is the road to the telescope like? So it's an 8-mile drive. Sorry for doing miles. It's an 8-mile drive. The first 4.5 are unpaved. So depending on if they've graded the road that day or not, it's bumpy. And then the last 3.5 are paved. The reason for that is when we get snow, we mostly get snow at the top of the mountain. We drive Ford Expeditions with roll bars because the road can be treacherous. The biggest issue that people have on the way down is that your engine isn't effective. Your brakes don't cool as much at high altitude. So you really need to drive down in a lower gear in 4-wheel drive, not because you're like off-roading, but because that gives you the better traction so you don't slide off the mountain. And going to Angela's question, it really depends on if the volcano erupts as ash and material. It really depends. And I say that because we lived through the Kilauea volcanic eruption that many of you saw on television in 2018 with no impact to our observing. That being said, we did observe on our webcams a massive bloom, a massive ash cloud that actually broke above the inversion layer before eventually settling back down. We don't know though. So we actually had these patches that we stuck like sticky stuff on our catwalk so that we could see if we ever detected falling ash. There's a lot of work in progress. What we did do during the eruption was lower our humidity levels for closing, just in case there was sulfur dioxide in the air. We didn't want that to combine with water vapor to basically have sulfuric acid on our maps. So Keith, allowing for upgrades, what is the lifetime of a facility like Cfht? Well, we're 40 and we're going strong. Our most recent instrument, Spiru, was brought online in 2018. So we have years and years that we can use Spiru for. The bigger answer to that question is one of the projects that we're actively working on at Cfht is called the Maunakea Spectroscopic Explorer, or MSE. And MSE is our plan to reimagine Cfht as a 10-meter telescope. Because we were built in the 1970s, our pier can hold the weight of a steel telescope from the 1970s, which is about the weight of a 10-meter class telescope today. So we don't have to disrupt any cinder. We don't have to put a new pier in, but we can put a larger telescope in a larger dome. And the plan with MSE is to do 3,000 spectroscopic fibers in one pass. So we'll have 3,000 fibers. They can be the spectroscopic follow-up to all of these really big space missions and surveys that we're seeing. The Vera Rubin Observatory is going to give a ton of targets. Gaia, TESS, the Euclid, all of these surveys are going to need a spectroscopic follow-up. Brandon, I'm not quite sure what you mean by how does Cfht compare to other facilities on the mountain in terms of size, in terms of je ne sais quoi, in terms of staffing. So if you could clarify in the question, I'll answer Gary. No, Gary, people do not stay overnight at the summit. If for some reason, like when we were doing our re-illuminizing, where we were taking the coating off of our mirror and putting a new shiny coating on, we did have staff that stay at the 9,000 foot level. That's about as high as you want to regularly sleep, because you can inadvertently stop breathing at high altitude while sleeping. It's just your mind and your brain aren't working together. We do have some of our remote observers who actually stay at the CFHT guest house in Waimea during the day. They live in Hilo and don't want to commute back and forth while tired, so they do have those accommodations. So no one at the summit, no option at the summit, but if you need to at 9,000 feet because of technical issues, or in Waimea because you're observing. All right. What observing is done during a bright moon like today? We use our infrared imager or our infrared spectrograph. So with WeirCam, the infrared imager, we can very easily observe with a full moon. We just have to have, a certain distance away from it. Similarly with Spiru and Espidons, which is our optical spectrograph, both of our spectrographs we can have bright time. We just have to stay away from the moon. Dark time is generally reserved for Megacam and Tate. Brandon, thank you for clarifying in terms of size or niches. So we are a 4-meter class telescope. The other telescopes on the mountain, Gemini's an 8-meter, as is Subaru. We've got the twin Kex. We've got the James Clerk Maxwell telescope, which is a 15-meter sub-millimeter telescope. That and the sub-millimeter array next door were responsible part of the Poveihi team. Our niche is wide field imaging and high resolution spectroscopy and Q observing. So where we really set ourselves apart, and prior to the rise of ALMA, I think ALMA will blow everyone out of the water here very shortly, but CFHT is the second most productive facility on Earth. And all of that comes from our large surveys. So the idea that 50% of our papers are actually archival. Because we've done these surveys and really established these astonishing data sets, people can go back and use them and continue to do science for years and years and years. We also, with our high resolution spectroscopy, Espidons and then Spiru, both of those are really, really big niches. Another more precise niche that we have is Megacam is really great in ultraviolet light, the purple. So the other large imager on the mountain, Hypersuprime Cam at Subaru, it's a larger field of view, it has more pixels, but it's really optimized towards the green-red end of the spectrum. Well, we're optimized a little bit more towards like green to blue. Both optical imagers, Spiru Hypersuprime Cam just goes a little bit more into the IR, and we go a little bit more into the near ultraviolet, which means that we're able to be a collaborative partner with programs that are on Spiru. So if you're a University of Hawaii astronomer who's using Tate, sorry, I'm giving my instruments. You are an astronomer using Subaru at Hypersuprime Cam. You can then come to CFHT and do that exact same field of view, but in the U band, so something that's much more purple, as opposed to a greener centered filter. I hope that made sense. I felt a little wobbly at the end.
Yeah, no, that's great. Mary Beth, I wanted to ask about the 30-meter, and you're living in Hawaii, obviously very close to the whole project. Can you give us an update on the 30-meter project?
So, I'm going to have to say I know about as much about the progress of the 30-meter telescope as you all. They took a pause during COVID due to COVID. So this time last year, there were a small number of protesters who were still at the bottom of Maunakea, not blocking the access road, but there. And at that point, when COVID hit, TMT came out and basically said, look, there's no way that we're going to be able to do construction this year because of COVID. Most of the remaining protesters, also because of COVID, dispersed. And so as far as I know, TMT is moving along in terms of, I follow them on social media, they're in terms of their technical progress, in terms of, building on Maunakea, all of that has been paused due to COVID.
Okay, with James Webb coming up, I'm wondering if CFHT has any plans to collaborate with any James Webb projects.
Absolutely, because there's a large Canadian user base for James Webb Space Telescope. The University of Montreal actually has a fairly large part in some instrumentation on James Webb. I am certain that we will be asked to do spectroscopic follow-up with Espérance on targets that they identify with James Webb. To answer your question, Ron, what is the most productive telescope? Period, it's Hubble. On Earth, it's the Keck observatories. So they take the number of Keck publications and cut them in half, 2 telescopes. And so that makes Waimea the most astronomically productive town on Earth, because number 1 is Keck and number 2 is Cfht. We're a town of 12,000, and our director really, the day that he saw that graph, there was a literal cockfight on our front lawn because there were 2 male chickens that were like fighting for territory. And he just had to turn around and laugh. You know, he's got chickens, there's a feral cat, and this is the most astronomically productive town on Earth. And it's cowboy country. We're Paniolo, we're rural.
Well, Mary Beth, I want to thank you very much for this great overview of the CFHT and taking your time out today to talk to us from the telescope. I wanted to ask Swapna to officially thank you for addressing us today.
Yeah, thank you very much, Mary Beth. It's been a pleasure. There's been some great feedback on the chat. We've had 55 people join us, a record number. So, you know, clearly a very interesting topic for everybody. Really thank you, Mary Beth. It's been a pleasure, you know, speaking to you, and what an interesting presentation. And, you know, Maunakea Scholars it sounds really amazing. Thank you very much for joining us today, Mary Beth. Look forward to seeing you again.
Thank you so much, and thank you for the invitation. And, you know, there have been an incredible number of negatives with COVID, but I think one of the positives that has kind of come out of this is the idea that we can still be connected even though we're remote. You know, I don't know when I would have had the opportunity to talk to your RASC group unless there was a CASCA meeting in Toronto and we were able to make it work out. So I'm really grateful that you were able to invite me, and I hope you enjoy Lori's talk in September. So mahalo for the invitation. It was lovely to talk to all of you tonight.
Mahalo, Murray.
Right. Have a great holiday weekend.
Thank you. And please keep an eye on our social media for this 3D tour to come out. Sorry, 360 tour, not 3D. 360,
yeah. No, we will post the video, and it has all of your social media links, and so we'll definitely keep track. And I very much would like to, I think many of us would like to visit the summit sometime, so hopefully we'll be able to do that.
All right, I look forward to seeing you all. Have a lovely weekend.
Thank you, you too.
Bye.
Bye. And let me just talk a little bit about our upcoming meetings. 2 weeks from tonight, we have a potpourri. And so if you have any presentations that you would like to give now with the nice weather, and any observations or short talks on anything astronomical, please let me know. I'll send a note out via email, and you can let us know if you would like to present to the group. Finally, our next speaker night, we're going all the way from Hawaii to Florida, so we're really taking advantage of Zoom. A friend of mine that I got to know a few years ago, Emily Carney, is a space historian, and she is she's an expert on the Skylab space station. And so I asked her to talk to us about Skylab, which was launched nearly 40 years ago, and or 50 years ago, I should say, just after the last Apollo mission. This was America's first space station. 3 groups of Apollo astronauts spent 1, 2, and 3 months up there. And it's interesting, a couple space conferences that I've been to, she has chaired group sessions with many of the Skylab astronauts, and learned a lot about Skylab. So she's going to share her expertise with us in a month from now on the 23rd of April. And we're very pleased to tell you that a member of the ROM Society, Kim Tate, who is an astrogeologist, she's in charge of the meteorite display and collection at the ROM. She's also involved with the Mars Sample Return Program. She's actually planning now for when the samples, which will be collected by the current rover Perseverance on Mars, she's starting to work now on how to handle those samples when they return to Earth 10 years from now. So she was hoping to give a talk to us live in person a year ago. I had her all lined up, but unfortunately that didn't happen. So she's going to talk to us via Zoom, and that will be our May talk. So that's all I have. Are there any announcements or anything that anyone wanted to say before we get back to our Friday night and our weekend? Okay, well then take care everyone. And again, if you missed part of this or want to review this, we will have the talk up on the website in the next few days. And I wish I knew more Hawaiian apart from aloha. And again, thank you for attending this this talk today. This was really a pleasure. And again, thank you, Swapna, for reaching out to CFHT to make this possible. So good night, everyone.
Andy.
Yeah.
Take care.
Good night, everyone. Aloha.
Bye.
Good night, everybody.
Bye.